chemistry class this evening. So we'll be taking kinetic theory of matter. Now, under the kinetic theory of matter, we'll be considering what the kinetic theory of matter is, the states of matter, change of states, and phenomena supporting kinetic theory. Please, while the class is going, let's try to take down notes and possibly we'll have questions that would answer later. Now, first of all, we have some keywords that we have to analyze under this topic. They are let's just kinetics and then matter. Please, who can help us with the definition of matter? Let's start with that. If you can, please just unmute and answer because I'm sharing my screen. I can't really also see whose hands is up.
Can you hear me?
Yes, please.
Okay. Matter is anything that have space and matter is anything that matter can be defined as anything that have occupy space and getting here from. Okay, I've forgotten, sorry.
Oh, you've done so well. You've gotten one part of it. You've gotten one part of it. You've gotten a part that occupies space. Now, I need another person to add to that, please. Yes.
Matter is anything that has weight and occupies space.
Thank you. I love that. Now you've added something to it. Weight. That is nice. Is there another person that has anything to add to it? Okay. If there is, yeah. Okay.
Matter is anything that has weight and occupies space.
Thank you very much. Also, you still mentioned weight. Thank you. Now, while I would want to accept that matter is anything that has weight and occupies space, we have to go back and differentiate between weight and mass. Please, let's take this down. Mass is everything that makes up a particle. Everything that makes up a particle is its mass. While weight, weight is everything that makes up a particle. Yes, weight is everything that makes up a particle. While mass is everything that makes up a particle with the force of gravity acting on that particle or that body. Now, what do we mean by this? Please, does air have weight? Like when you blow air into a balloon or you just blow air into the atmosphere, does it have weight? Do we get the question? Air does not have. But something like water or your solids, your table, your chairs, your phone, those things have weight. So the air also is a form of matter. Gases are forms of matter, but they don't have that weight. They cannot really stand on their own. So it is preferably to define matter as anything that has mass and occupies space. Because the force of gravity does not act on air. Do we get that?
Yes,
force of gravity does not act on air. And you know that air does not have weight. So please, while we have been taught that matter is anything that has weight and occupies space, let's try to correct that notion this evening, as matter is anything that occupies space. Now, in physics, I don't know if you've been told that the value for gravity is 10, right? 10 meter per second squared. Now,
Yeah.
for you to now get the mass of, for you to get the weight of an object, you have to multiply the mass times the weight. For example, times gravity. For example, when you go to the hospital to check your weight, what you actually see is the force of gravity that is dragging you and keeping you on top of that scale, multiplied by the force of gravity. Because you as an individual, if you should move from Earth to Mars, you know you cannot stand, right? You will continue bouncing from one spot to the other. But it doesn't mean that you don't have particles in you. Well, because the force of gravity in Mars is totally different from the force of gravity on Earth. That is why you will be bouncing. But on Earth here, that force drags you down and doesn't allow you to skip from one part or from one point to the other. So I hope the point is taken now. Matter is anything that has mass, please, mass, not weight, and occupies space, because air is also a form of matter. All gases are also forms of matter, despite the fact that they do not have weight. Now, with that being said, we now move to the kinetic part of it. We do know that when we are mentioning the type of energy that we have, one of the type of energy is kinetic energy, and we also have potential energy.
Energy.
Now, so now, what is kinetic energy? If someone has the definition of it, please, you can just say it out.
Can
I do not
I read?
remember. Yes, please. Yes, please.
It's showing here. Can I read from here, from the screen?
Dear, I did not put what
Here,
kinetic
sorry,
energy is.
here is kinetic theory. Sorry.
Yes, that's what I'm saying. So, what is kinetic energy? Okay, let's just let me just move on. Delay much. So, kinetic energy is energy possessed by a body in motion. Kinetic energy, that energy possessed by a body in motion, where potential energy is the we are trying to get from here is that every particle has kinetic energy. What we are saying is, even the fact that your phone is sometimes in a position at a particular point in time, the particles in it, the particles that make up that phone, have kinetic energy. Despite the fact that mountains and rocks look like they are unshakable, excuse me, and in a fixed position, there are particles in them that have kinetic energy, that are in constant motion. Combining matter and the kinetics together, we have the kinetic theory of matter, which states that all matter is made up of very tiny particles which are in constant motion and possess kinetic energy. All matter, every form of matter you can think of, including you as a person sitting down in front of your phone or holding your devices. You are sitting down, but remember, you have your blood circulating around your body, right? That is a particle inside your body. You have cells moving constantly in your body, being rebuilt, some dying, some coming to life. You have, even inside the cells, activities that are going on. So even though you are exhibiting some form of potential energy right now, the particles that make up you as an individual are in constant motion. Some moving very fast, some moving slow, some just vibrating at a point, but they are always in constant motion. Please, let's try to keep this also at the back of our mind. Kinetic theory of matter states that all matter is made up of very tiny particles which are in constant motion and possess kinetic energy. Now, we'll move now to the state of matter. Please, if you have any question, let's just keep it to when I'm done sharing the screen so I can pick those that want to ask questions. So there are three states of matter. We have the solid, liquid, and gas. I arranged it here, solid, liquid, and gas. But specifically here, we are using water as the practical example of these three states of matter. You notice I used three different colors to indicate the change from which ice changes to the liquid form, which is water, before it changes to the gaseous form, which is steam. Now, what happens is this. Your ice crystals have very low temperatures. Could be around 0 degrees Celsius, could be 1, could be 2, could be 3, could be 4. But the moment whereby the temperature begins to increase, either you are now boiling it or you've brought it out and heat around it start to have effect on that water. What happens is that, on that ice crystal or ice cube or ice block, what happens is that it begins to what? Melt. And as it begins to melt, it now changes to the liquid form. When you apply more heat, for those of us that already know that the boiling point of water is 100, by the time you apply more heat and the water begins to dissolve, after dissolving, it begins to boil. By the time it gets to its boiling point, what happens? You start having vapor form. Now, practical example of this is boiling your water. Possibly you want to take your bath and you put your water on your heater and then you maybe forget about it or you are busy doing something else. If we are those people that forget for long, or maybe you've gone on an errand, if you don't come back on time, what will happen to the pot or the kettle?
To dry it up.
Beautiful, to be dried up. What has happened? That water that was inside has been converted to what? Vapor or steam. So the point here is this: for there to be a change of state of matter, there has to be change in temperature from cool to heat. Most matter actually undergo this process, including your jewelries, your gold, your silver. Initially, they were in solid form before they were melted, and melting it means it has been converted to a liquid form before it now solidifies back. So there was a change in temperature from the heat to cool. So initially they were solid form, let's say they were cool, and then when you now heat it up, it liquefies before it now changes to the solid form back. So most forms of matter actually undergo these processes depending on the amount of heat or the amount of cold that acts on the form of matter. Move to the next slide. What are the differences in these states of matter? Let's start with solid states. For solid states, most solid or all solids are held by forces of coercion. Now, these forces of coercion determine how strong the solid will be. The force of coercion between the particles that make up your ice crystals and the particles that make up, say, stone, for like granite, is totally different. Because you notice that it is easier to break down that force of coercion between the particles that make up your ice crystal and then comparing it with that of stone. You notice it is harder to break stone. So the fact that all solids have a force of coercion, the forces of coercion still differ, but these forces of coercion keep them fixed together. Now, what about liquid states? For liquid states, yeah, they have force of coercion, but it's not as strong as that of solids. They are kind of free and they move around gently, like slightly. But in the case of gases, the force of coercion is totally negligible. That is why gases just move around. For example, if you are in an area whereby you're experiencing a lot of wind, say you're in the north or thereabouts, You know that whenever the wind comes, wow, it's usually very heavy. It's all air, but then it can be hitting you left, right, and if you're not careful, well, some people say it can actually carry you away. Or say you go to the beach, the way the breeze hits you here and there, the way it touches your skin, the way you feel it, yes, it just moves randomly because there is no force of coercion, or the force of coercion is very negligible. Now, what about kinetic energy? Kinetic energy in solids is actually the least there. What do you mean by that? The particles inside that make up these solids, they move, they vibrate in a particular spot, but the energy they possess is not strong enough. Comparing that to liquids flow. Is that not so? Say you
Yes.
pour out a cup of water, a cup of oil, or whatever, it flows. Why? Because yes, the kinetic energy is there, but it is more than that of solid. The particles can flow because the kinetic energy is there, but not as strong as that of solid. Also, it's more than that of solid. Now, what about for the gaseous state? It has the most kinetic energy, very, very vigorous. In fact, the way they explain it is that the gases move so random that they hit the container in which they are kept. So random kinetic energy. Kinetic energy in gases is very, very strong, very, very high. Moving to the shape, solids have fixed shape and volume. We all know that. Once you see a solid, you know it has a shape. Then for liquids do not have shape, but they take the shape of their container. And for gases also take the shape of the container. But unlike liquids, gases occupy the entire volume. What do you mean by this? I know many of us have played with balloons. Have you ever blown your balloon and you notice that the air will just go and rest on one side of the balloon? Has that ever happened? I need answers, please. Like the air will just rest on one side of the balloon.
No.
Exactly. It fills the entire balloon at once. The more air you put in, the more it expands the balloon, right?
Yes.
But what about water? If you have a 75 cl of water to pour in a 1 liter container, no matter how, it will just go to where it should stay. It cannot fill the entire volume of the container. Now, what about density? How heavy and compressible are these things? For solids are dense, they are heavy, they have weight, and you cannot compress them. You can't force them to change shape by just say squeezing. Say, for example, you try so hard to squeeze your phone. What happens? Phone breaks if you use excess force. Say you decide to put it in something that will squeeze it very well. Phone will break. You can't compress it. But what about liquids? Yeah, liquids are not as dense as solids. However, they are also not compressible. But for your gases are compressible and the least dense. They don't have weight. Now, you might tend to ask, how can you compress gases? Your gas cylinders at home. You notice that, say your gas cylinder is empty. By the time you take it up to go and fill, you shake it. What they told you they put is gas, but you feel that there is water inside now. Is that also?
Yes.
Exactly. So it has been compressed. It's that force of compression that now makes that gas take the form of a liquid because it has been seriously compressed. It's the same thing with lighter. This lighter that we use to say it's not the normal lighter that you just strike it and fire comes out of it. That lighter, when you look at what it says, it's like it's water. But the moment you break the lighter, what happens? You don't see any water. It's all gone. It's because it's just gas. But because it has been compressed into that container, it has to take that form so that it can actually stay within the container. So I hope that we've taken note of all of these all of these differences between the.
Very well, sir. I'm really enjoying the class.
Sorry?
I said very well. I'm really enjoying the class.
Well, we thank Jehovah for that. So we move to the next slide, please. Now, change of state. What causes change of state? A particular substance can exist in any state depending on change in temperature. We said that at the beginning. Now, these are the things that influence change of state: melting, evaporation, boiling, freezing, and condensation. Melting, evaporation, freezing, boiling, and condensation. Now, what is melting? Melting is when a solid is heated and then its particles acquire more kinetic energy and it begins to vibrate. And this happens when it gets to a temperature called the melting point. By the time you put your eyes, say you want to really drink water, and then it's iced already, you want it to melt. By the time you put it in a pot or kettle or whatever the case may be, the heat begins to work up on it, but it doesn't melt immediately, like it doesn't just go down immediately. First of all, these particles have to acquire more kinetic energy. They have to vibrate more. And what to supply that vibration is the heat that is being brought up. So they vibrate more. The more they vibrate, the more they acquire more of that, that energy that is required for it to now collapse. So by the time it collapses, it now changes from the solid form directly to the liquid form. So like I said, the temperature at which this happens is called the melting point of that substance. But then there is something. There are some substances that change directly from solid to gas. They don't go from solid to liquid. They just melt and change directly. Practical example is camphor. Camphor is that white, most times they are balls, they're like balls, they sell them in the market. I don't know if we've seen them. They're usually whitish. You put them in your rooms, right? And other bigger forms of it is your drummer boy, your sunshine. Now, these things, let's say you buy drummer boy today, you open the nylon, put it in the pack, and you come back and check after 2 weeks or 3 weeks. Is it the same size as when you put it there initially?
No.
No. But do you ever notice that there is water inside the carton? Is there ever a form like maybe when you open it, you see something like water inside it? If you've not noticed, no matter how, you will never see anything like liquid inside. Because what happens is that camphor or that drummer boy or that sunshine changes directly from solid to gas. And that change of state is called sublimation. When a substance changes directly from solid to gas without moving through the liquid phase at all, is called sublimation. Now, this is it about melting. There has to be increase in temperature. Please, let's take note of that. There's been an increase in temperature, which will exert more kinetic energy. And then the more kinetic energy that comes in, the particles that make up this substance begin to vibrate. And when they get to melting point, they change from solid to either liquid or solid directly to gas, which will be called sublimation. Now I'll move to the next one. Evaporation. Now, the difference between evaporation and melting is that evaporation occurs at all temperatures. Yes, there is still they have to still acquire more kinetic energy and they have to change to a different state. Now, why do we say it occurs at all temperatures? Normally for your, let's say your water, as we said initially, you boil your water. By the time the temperature rises to a certain degree, the water, you see it coming out of your kettle, it's evaporating, it's forming vapor. But What about when you apply methylated spirit to your skin? What happens? Does it remain on your skin?
No, it dried
Did
up
your food
immediately.
boil it?
You say?
The methylated spirit? No. What happens is, for something like methylated spirit, it undergoes evaporation at very low temperature. It doesn't need to acquire a lot of heat. At low temperature, it can just change directly to gas. So evaporation occurs at different temperature and is affected by, number one, the temperature of the environment, and number two, the type of substance involved.
Hello,
Like
sir.
the example I gave. Yes, sir.
Sorry, sir. You have less than 9 minutes to go.
Oh my God. Okay. Then let's just move on fast. So when it comes to, what about when it happens in a closed container? For a closed container, evaporation, say your pot now, you have your pot and evaporation is taking place. You notice that if you open your pot that has water inside, on the top surface of your cover, you see water that's gathered there. For it to have gathered there, what happens is that it has condensed. It has changed directly inside that container from the liquid form to the gas, but because there was no way for it to go out, it now condenses. So that is condensation. This is the same thing that happens in the atmosphere. When water goes up to the sky and then it condenses in the cloud, when the temperature reduces, it comes back as what? Rain. Now we move to boiling. For boiling, happens at high temperature, obviously. And what happens is, for substances to boil and escape, it has to have broken down what we call the vapor pressure. Now, this vapor pressure is what allows for it to change from this liquid form to gas. The moment it starts breaking that vapor pressure, evaporation begins to occur, and that means it has changed from the liquid form to the gaseous form. Now, freezing and condensation. When cooling continues, it gets to a temperature called the freezing point. And then for some cases, it's also called the melting point. So when you see freezing point, is the same temperature as the melting point. Now, the energy required for things to freeze is called the latent heat of fusion. That is, that the energy required for your particles now in that liquid to come together and become solid is called latent heat of fusion. And the temperature has to be very low for this to happen. Now, the reverse of this, that is for that frozen solid now to now come back or condense to become liquid, is now called latent heat of vaporization. So when you are trying to heat that solid and change it back to liquid, it must have what is called the latent heat of vaporization before it now melts down and becomes your liquid. Now, these are the factors that affect change of state. Now, quickly, we move to the phenomenon supporting kinetic theory of matter. There are three phenomena supporting kinetic theory of matter, which are the Brownian movement, diffusion, and osmosis. Diffusion and osmosis, I'll take that very fast, is the movement of molecules from a region of higher concentration to a region of lower concentration. But the difference between osmosis and diffusion is that for osmosis, there must be a semi-permeable membrane. Quick example, I want to differentiate between osmosis in two different substances now. Osmosis and diffusion. For example, you have those of us that prepare moi moi or akara. We know that for us to prepare moi moi, most of the times, we might have to soak the beans, right? Now, soaking the beans, by the time you come back, you see that the beans are swollen up, meaning it has absorbed the water. So the water has moved from inside the bowl where it is concentrated to inside each seed of beans where it has least concentration. And the semi-permeable membrane here is the coating on the beans itself. So that is a practical example of osmosis. And for diffusion, when you use your perfumes, for some of us, when we are walking on the street and then, wow, maybe somebody passes us and the perfume is just so nice. That person has used the perfume since at home, but the person is walking on the street and the perfume is still following him. What happens? He has the concentration on him or her, and the more he moves, he disperses this concentration around the environment. That's why you are able to perceive it. So it's moving from him, which is the region of higher concentration, to you, where you have the region of lower concentration. So that is diffusion and osmosis. Difference being that for osmosis, there is semi-permeable membrane, and for diffusion, there is no membrane. Now, what about Brownian movement? Robert Brown discovered this in 1827, where he observed the zigzag movement of a pollen grain in water. Like he observed it under a microscope, actually. So he put a pollen grain on, say, a drop of water. Yes, exactly. A drop of water, and observed under the microscope. Then this pollen grain was moving, despite the fact that he was not shaking the table or anything. What was happening? The molecules or the particles that make up the water were moving. So as they were moving, they were hitting this pollen grain. Please, you can also test this in your houses. You have a cup of water and you put maybe tiny speck of dust inside that water. Observe very well. You notice that that speck of dust is moving. That is Brownian motion. So these are the three things that support kinetic theory of matter. Phew. Okay, now we've highlighted, this is all I said we're going to discuss today. So I have some questions to ask by way of revision. Now, these questions actually come out in your past questions. I saw them from some past questions. So that shows you that this topic is very relevant. And the first question here is, the droplets of water observed around a bottle of milk taken out of the refrigerator is due to the fact that A, water vapor in the air around the bottle gains energy from the bottle. B, temperature of the milk drops as it loses heat into the surroundings. C, saturated vapor pressure of the milk is equal to the atmospheric pressure. And D, water vapor in the air around the bottle loses some of its energy to the bottle. Now, based on these three phenomena we have discussed, what is the correct answer here? I need the answer. Anyone? Yes, let me hear it.
B, temperature of the milk drop as it loses heat into the surroundings.
Yeah, that's nice. That's a nice try. So are you telling me that the bottle allows for water to come out of it? Because that would be the meaning of that answer. It's a nice try. I like that though. Does any other person want to try, or do you want to try again?
I think it's D.
Beautiful. Thank you. That's correct. So the vapor pressure around the air, you know, the inside of the fridge is very cold. So the more, yes, the particles there in random motion are moving, but at some point, some of them will lose some of the energy, and then it will now rest on the bottle. Is that clear? So this was taken from JAM question 2010. Now the next question.
Okay.
Which of the following properties is not peculiar to matter? Not peculiar to matter. A, kinetic energy of particles increases from solid to gas. Random motion of particles increases from liquid to gas. Orderliness of particles increases from gas to solid. And the last one, random motion of particles increases from gas to solid. Which is the correct answer?
A.
Kinetic energy increases from solid to gas. Not peculiar. So that one is peculiar to it. So that would be saying it is peculiar to kinetic to matter. So no. Yes.
C.
Orderliness.
Increase from gas to solid.
Well, that is part of the peculiarity. So that's not the answer. Remember, not.